Good afternoon and welcome to today's webcast. On behalf of Quest Software and Programmer's Paradise, we'd like to welcome you to the Spotlight on Oracle SQL Performance, Predictive Approach to SQL Performance Tuning webinar. During our webinar, I'll briefly cover who we are, give you a company overview of Programmer's Paradise. Then over to Scott Stone, Senior Product Manager for Quest Software, which is the Quest Spotlight database product. We will go to a question and answer seminar and follow up with a summary. Paradise has been in business for over 25 years as the leading reseller and developer of infrastructure tools. We specialize in providing Quest software solutions for application management, Windows management, virtualization management, and database management. We provide database and modeling and infrastructure design and training services. Our database worldview software ecosystem is designed in-house and provides you, the end user, insight into industry-leading tools for end database needs. If you look at the hexagon, you can see Quest is located in many of the hexagon components. And today we will be covering the performance monitoring and tuning section of Quest Software's offering. I'll turn it over to you, Scott.
Thank you. I wanted to, whoops. Thank you. For basically what we're going to cover today, as Sean said, I'm the product manager for the database spotlights at Quest. What we're going to talk about today is a new capability and a new approach that we've added into our Spotlight on Oracle product to do predictive SQL tuning. I'm a product manager at Quest. I've been a product manager for performance products, both at Quest and some other companies for about 15 years. The first thing to cover is what we currently do, what DBAs currently do in today's environment to tune SQL. It's the approach that we've used with our tools and most of our competitors use as well. It's primarily a reactive approach to diagnosing problems and resolving them as quickly as possible. We'll talk about why that's not sufficient today and why we need to do something differently. To do that, we need to talk about what sort of performance patterns you see in the SQL that as it's running and how it may change over time. So that a SQL statement that may be performing well today may not be performing well 2 or 3 months from now. To do that, we have to talk about what information we need to collect, and analyze that information in order to make some sort of prediction. And finally, over the approach that we've taken in Spotlight on Oracle to help you in this. So traditionally, reactive SQL tuning basically involves tuning the SQL initially in development environments. Development DBAs out there that specialize in this. The problem is that you can't tune the SQL perfectly in the development environment. You can try to reproduce the production environment, but little aren't successful in doing that perfectly. So basically, you tune it as well as you can in the development environment, throw it over put it in the production environment, and then wait till it has some poor performance. Then you call somebody who's complaining about your performance and request that you try to find a problem, and you need to find it quick. Approach to this problem we've traditionally called it detect, diagnose, resolve. In a quick environment, you would detect a problem first, probably with a continuous measure like Foglight, then to investigate that with a diagnostic product like Spotlight to get a deep dive analysis of what's going on, and finally try to resolve it with a product like a SQL tuning, or if it's not a SQL statement problem, you resolve it with something like code. Basically, what we've been focused on to this point is minimizing that amount of time when you actually have a problem to resolve it. And that's still important. Ideally, we would not we'd like to avoid those problems before you get the phone call. It means that reactive tuning approach is not cutting it today, is that the database vendors have made dramatic improvements in their optimizers. So there aren't very SQL statements left that resolve with some rewrites. More often they require some schema change and addition of an index or something more complex than just simply correcting some programmer's mistake in writing the SQL. The other that you've got stringent availability requirements today. We've always had to reduce planned and unplanned downtime, but the amount of planned downtime that is acceptable has been reduced over the years. So there's more and more demand for continual availability. So outages for schema changes or indexing require a lot of planning and a lot of lead time. And you're in a reactive approach, you really don't have that lead time that you need to make that change. We have diagonal scaling architectures. By that, we mean scale out or scale up. The applications today are designed for these scale outs or scale up architectures. Scale out, we mean things like clustering technology, racks, so that you could add a node and get more capability by just continuously adding more nodes. And scale is the more conventional approach of just getting more hardware, adding more CPUs to the same machine. But the problem with that is that the databases that are increasingly not as scalable as the applications in that respect. You can't just take the database and throw hardware at it and expect it to always get a payback for that additional hardware. We find that the SQL performance is still the number one performance issue in regard to databases. And again, databases are the most important, or the most critical performance layer in most applications. Just about, most of you probably, just about every application that most people are familiar with has a database underneath it. Advances in I/O technology are not keeping up with the increases in storage, CPU, and memory capacity. For a long time, we've assumed that the advances in hardware will keep up with the advances in software and will just keep pace. But it's not across all technologies. They're not all keeping pace with each other. Database is the least capable of scale out, as we talked about. SQL performance is the most important. We have tools, including Spite, that help us define and resolve internal contention points within Oracle, and try to resolve those. Most of those contention points are associated with poor SQL that's coming into them. That's causing a problem. And we just about that the SQL can often increase faster than hardware upgrades can respond. A lot of times I've heard people say, hardware is cheap, memory is cheap, disk is cheap. All those are true, but if in the real world, it's often very hard to get hardware upgrades in place as fast as we need them. Any of us that work in a large company can attest to that. Just because disk is cheap doesn't mean that I can instantly get more disk assigned to my account if my ICS department will not support it. The application demand is primarily expressed by the SQL. The application is always actually putting a load on the database system by the SQL generates against it. And we talk I/O getting slower. It's only getting slower. It's getting relatively slower to the other constraining elements of your system. In the last 10 years, this chart shows us percentage increase over the last 10 years in each of these areas. While I rate has improved by about a factor of 400%. Disk capacity has increased by a factor of 20. So while 10 years ago, or you may have been getting 20 IOs per second, today you get 100 IOs per second. But Harrison may have been getting a gigabyte of disk to access. 10 years ago today, there's 200 gigabytes. The net effect of that is the IO capacity relative to the disk capacity is decreased about 500%. Similarly, the CPU capacity has increased by a factor of 32 over the last 10 years. So the situation is even worse in that respect. The I/O rate relative to the amount of CPU capacity that we have on machines has gone 800%. So more the bottlenecks are being centered on our ability to actually write and read from the disk. We've assumed that SQL is the most important, and it's the first thing we should look at. But why do we believe that? And we show how SQL is basically going into a system or database, and that system is trying to minimize the actual physical I/O by using caching in memory and managing the requests internally. A lot of you may see a problem where a particular disk is getting a lot of traffic, and we talk about managing that and trying to distribute load across disk, and all those things are needed. But there's no point in optimizing how your disk performance is working if you haven't first resolved the SQL that's coming into the Oracle system and the contention for the resources in Oracle itself. So really, the approach that we use is that you should go from the left to the right, the methodology, and first make sure that you've got your SQL normalized and tuned as best you can. Then try to normalize and tune the actual Oracle database to reduce contention. And then finally, once you've minimized the full I/O as much as you can coming out of the Oracle system, then worry about actually managing the physical I/O. Big performance patterns. You may or may not have heard of this terminology. The Big O regards how a computer algorithm will vary in performance based on the amount of data that it has. We see several patterns represented here. The orange line at the bottom is 1. That's a constant. That just means that your performance doesn't vary with data volume. That's an ideal situation. The purple line or light or lavender line is a relationship. That's more, meaning as your data volume goes up, your performance goes down with a relationship. Logarithmic means that you're getting a lot of, when you start out, things get a lot slower initially, then you sort of level out, and then you don't get very much increase once you get to some level of performance. And first is exponential, where we are increasing our performance is going down at an increasing rate as we add data volume. So that's the one scenario that we want to be most worried about. SQL performance patterns fit into these different categories in some predictable ways. The first one pretty much represents a perfectly balanced hashed index or table. So you're basically doing one I/O no matter what your query is, going for the primary key. But the problem is that you have to rebuild the index constantly to make that work, and that's not a viable alternative. When by definition we're talking about increasing data requirements. So that's good for static requests, but it's not going to address most of our problems. That's what we get when we have full table scans or index range scans. So the data increases, we needed to scan proportionally more data, and therefore performance goes proportionally down. There we go. Logarithmic, represented by a B tree index. We have some degrading in performance, but then it takes longer and longer to get to the next level of the B tree. So if you go from level 2 to level 3, it takes from 100,000 rows. To go from 3 to 4, it's 1 million rows. From 4 to 5, it's 1 billion rows, and then you may never get to level 6. So see a decrease in performance as you move up in level, but it takes longer and longer to get to increasing levels as you get larger. Exponential, that represents a couple of different scenarios. Linear operations where for every row of a table you're reading another row of another table. And commonly, linear operations executed at an increasing rate. So, if you have SQL that is by itself has a linear relationship in its performance, but you are executing that SQL statement that much more frequently as time goes on, the result will be an exponential relationship. SQL statements contain multiple steps, and the least scale step will ultimately dominate the performance of the SQL over time. We talked about linear data can turn exponential if they're associated with increasing execution rates. So we'll now about a predictive methodology that this whole presentation is about. The first thing I have to do, obviously, is collect the performance data. Look at the performance data for the SQL statements, determine if there is a trend or is there a relationship. What type of trend do you have? What category does it fall into? Linear, logarithmic, exponential, constant, or is some other curve that it fits better? A static curve for that particular data. Determine up in range, we need to know not only what is our projection for the future performance of the SQL statement, but also how confident are we of that projection, so that if we are looking into the future and we predict that they'll hit a certain level that'll cause a problem 2 months from now, we want to know if there's a possibility we can reach that point 1 month from now. For discontinuities in the data, we'll talk more about this. We have to look to see if there's been a plan change. If there is a plan change for the SQL statement, then any trending is sort of irrelevant because it's really 2 SQL statements as far as the internal system goes. So we're aware of that. Tune SQL to get the performance improvement. So what to measure? All the information that you need is contained in the $SQL table in Oracle. It contains all the data that's needed. Different criteria you can use for measuring SQL performance are elapsed time. A lot of people that because that's what the user's experience actually goes on, as long as it takes the SQL to complete. CPU time or physical I/O, we talked about those as being measures of resource consumption. We allow you to do any of those, but the one that we prefer is logical I/O. And logical I/O is usually the most sensitive. It's the least noisy measurement of cost. Time, CPU, and disk I/O, all of those can be affected by other things that are going on that are not related to the SQL statement that you're actually studying. On what SQL statements are running, how low the system is at the time. Those can vary based on things that have actually nothing to do with or how much is in memory, how often does the does the writing to physical disk. Those can vary based on things that have nothing to do with the SQL statement. With both the overall costs for the SQL statements for all executions and the per execution cost. Now, the techniques we use to predict, we found that we can use just standard statistical methods. First is correlation. If there's no relationship at all, then there's no point in trying to do a prediction. So first you have to decide, is there a correlation over time with the SQL performance? Do a linear regression if a linear is the best fit, or a linear regression. If we have a fit that's either exponential or logarithmic or something else, then we need to know that as well to do a projection. What's necessary is to do normally a cyclic series analysis. It requires long-term data, and that sort of analysis is, very long-term data. That analysis is typically used when you're trying to find seasonality or cycles in performance. You're trying to figure out what's the performance at month end or on a day or anything like that. Well, that's not what we're really trying to do. We're just trying to look at degrading overall SQL rather than predict performance at a specific point in time. Q-query is another more complex method. Involves trying out what happens when you exceed 100% of CPU utilization. You can't extrapolate very well from that from the historical data. And, for the most part, our methodology tries to avoid executing in the first place. So we're not trying to find out just how bad it's going to get when everything falls apart. We're mostly trying to figure out what we need to address to avoid getting into a situation where we have excessive queuing. So we don't see a great deal of benefit in doing a very complex, precise but inaccurate of a future performance. So, what about the do-it-yourself approach? How would I do this if I wanted to? If I don't want to buy a tool and I want to try to just sort of figure out how my SQL performance is changing over time. As we talked earlier, all the data you need is in the $V SQL statement. This SQL statement gets the timestamp, the ID, number of executions, the logical is buffer gets, time, CU, physical reads, information you can get directly from the SQL statement. You can take that information and insert it into save it and insert it into another table, a history to work from. Then from that point, we need to look at a single SQL statement and start to evaluate it based on its future performance. In this example, we're getting the timestamp and buffer gets, which is logical I/O over time from our history. We can take that and bring it into an application like Excel to do some statistical analysis. There's some pretty statistical tools available in the analysis pack with Excel. I think it's an add-on that you have to, it doesn't come standard, but you can add it on to any Excel installation for free. In this case, we're calculating, we've got all the information in, so we calculate a logical I/O per second rate by taking the delta with a timestamp and the delta in the buffer get metric. Then we can plot that over time in Excel, and the thing we see is that we have some weird looking data. Usually that weird data is, and we see, we're highlighting a negative logical, which is obviously impossible. What that involves is times where the database restarts, or you have a pull flush, or some other thing is happening that you can't a counter ahead of time that's causing the counters to change so that the delta calculator not accurate. So you basically have to go through and move any of this anomalous data by hand. Once your data in and you've removed the anomalous data, you can use the analysis pack to do correlation. We've calculated a correlation coefficient of 0.587. Basically, it's going to give you a number between -1 and +1. +1 means every time goes up, the logical I/O also goes up. -1 means that it goes up and the logical I/O goes down. And any in between there means it's how well correlated it is. It's sometimes to know what is meaningful. In this particular case, we know that 0.587 is meaningful in the number, and the performance is correlated over time. So now that we know that we have a correlation, we need to fit the data to a curve. We plot that out, and we can use Excel to choose a curve and do a trend and add a trend line and project ahead with that trend line. But it's up to us to decide what kind of line we want to fit. And as you can see in the cloud of data there, often that's not easy to do just from sight. But sometimes it'll be obvious you have a linear relationship or logarithmic, but often you just have to make a guess and apply the best trend line that you think, or you may have to try different ones. There's a way without doing something practically to find out which one is the best fit. So there's a way to do the same thing within SQL. Use a lag function, which basically gets the last row of an ordered row, so we can calculate the delta and buffer gets using lag and the last time stamp and get a rate there. Calculate a correlation coefficient. I think these functions were in Oracle 9 or 9.2. You can get a correlation for all that data, and use the regression functions to get an intercept and a slope to do a linear regression. So using Excel or with Oracle, you can get some of this information for any given SQL statement. And we've addressed these as we went along. For this do-it-yourself approach are dealing with the database restarts and pool flushes. You have to figure out where these are and throw out the anomalous data. Determine what's in and what is insignificant correlation. Bring this error interval. If we fit, how accurate do we think that fit is? How closely aligned is the data, even if there is a curve? Is it a range of possible? Does it have noise in it? The plan and configuration changes. If you make a major change to the database, you really can't use the previous history of that SQL performance in your projections. So the plan that may invalidate your predictions, you need to be able to discount anything before any changes. And we talked about dealing with a single SQL statement. To do this, you really need to plan to do for hundreds or thousands of SQL statements, because you don't know which one is going to be the one that has a problem. And choose the line that best fits. That's hard to do just from using own intuition. So now let's talk about how we approach this with Spotlight and Oracle. This Spotlight and Oracle Expert, which is a bundle of Spotlight and Oracle with our SQL Optimizer product. This new capability that's available in that packet. It's also sold under the name Spotlight and Oracle Professional that has the predictive capability. So what you see here is a list of all the SQL statements. They can be ordered by any of the columns that are listed, the percentage of the total load now, percentage of total predicted, how fast it's increasing, what's the total cost increase. The icon to the left that you see is red or yellow. Means exponential, that's the worst case scenario. Yellow means linear. We don't see here, but if you have any green, those would be linear or constant. And gray would mean that there's no correlation whatsoever. And so there's no point trying to do a prediction. And also looking on the screen, see the text here basically lays out exactly what we're looking at for this particular SQL statement if it's hard to make sense of it. The first one in our list is an example that's currently 10th, but in 6 months, we're projecting ahead 6 months on SQL.io. It'll be our worst SQL statement. It'll be a 100x increase in cost. And again, this exponential increase is shown in the graph below. If the log.io per execution, we see a case where that we spoke about earlier. It's a really linear relationship, and the yellow dots you see here are the actual data points. We're plotting this line. We've got a pretty tight line in our executions. Our cost statement run over time, but we also see that the number of executions are increasing over time. So the combination of those two leads to an exponential growth in the overall demand. Also talked about the need to have some interval, some of accuracy to plot to understand how far we're predicting the SQL will go. Houston, we were very familiar with the cone of uncertainty when we're looking at hurricanes coming in. That's basically what we're talking about here. This is a 95% confidence interval along the line. So the reason that's important is you can if you want to be very conservative, you need to look at the top line rather than the middle line, and if you have some particular threshold that you don't want to exceed, you want to think about that top line rather than the most probable line, which is the middle. From Oracle, we can launch our from Spotlight, we can launch our SQL Optimizer product for that particular SQL statement. Our Optimizer product basically looks at the SQL statement and does automatically calculates alternative rewrites of the SQL statement that return the exact same data set. And then we look at the cost from Oracle that for the plan cost. As you can see, the plan cost for these different alternatives is all over the place. But we don't run the cost from Oracle. We actually run the SQL and look at performance. And as you can see, when we actually run the SQL, we only have 3 different actual costs here, rather than the different costs that they predicted. So first one involves adding an index. So the Optimum product will look for opportunity for adding indexes as well as rewrites. There's not that many opportunities for trivial rewrites, but sometimes there are. So we'll look for those, and we'll show you the one that has the highest improvement. So by adding this index, we get a 300x performance improvement in this particular SQL statement. And when we turn and run the same SQL statement, we see that the performance improvement is much improved. So we also need to talk about the problems of rejecting. That is, when you have change in plan or removal of an index that may change the plan that makes your projection valid. We automatically detect that, and we change the actual of the data points here. I don't know if you can see it, but some are yellow, some are white. So something's changed, and we sort of give you an indication that we think there's a problem. You can change the trend line by adding a trend change within the product. You can just, what involves is just taking off the old data that doesn't apply anymore and disking that and doing any of your projections. So you can use the slider to move the data point wherever you think is the point where you see a discontinuity, and put the trend change in there, and you can make a note about why you put that there. In future releases of Spotlight and Oracle, we'll do this in a more automated fashion to detect when we think there's a trend change and show to you just on the graph, but also in the list at the top. In the future, I mean, a few months from now. So to put the trend change in, we see linear growth. So it's not a big problem, not as big a problem as we thought it was. So another important thing, it's not just important to scare you about performance degradation. We also want to make sure that what we are predicting is accurate. So, to summarize, as we spoke about in the beginning, the SQL tuning alone can't address the needs of today's environments. It's not enough just to be fast. Sometimes the changes are required can't be fast and need some planning, so you can't just fix it after it breaks. The SQL can exhibit performance that will lead to exponential growth in resource demands. So today, something that's working fine in a month may just totally blow up. So those types of scenarios that we're trying to detect at time, the ones that are growing linearly are possibly a problem, but those are not going to blow up in your face suddenly. They're going to happen over a course of time, so you can see those coming better. And the capture of the $V SQL data and statistical techniques can be used to anticipate the future SQL performance. And although you can do a lot of this on your own from Excel or within data itself, reliable analysis requires more sophisticated software, because I'm sure most people don't want to go in and try to take out all the anomalies themselves, figure out what the lines are, which approach or which curve fit is best, and do that on an individual basis for every SQL statement that's currently running. At this point, I'm going to do a demo of the product to show you what I'm talking about. There we go. Share. I don't know Oracle product. This is if you're not familiar with it, I invite you to go online to our website and look at our flash demo. This is the signature home page, which gives you an overview of your Oracle performance right now. Basically, green good, red is bad, yellow is not as bad. And this is an architectural representation of how data is flowing from your sessions all the way down to your physical storage. This little side that looks like the CV side, that's our new predictive diagnostics capability. So I'll click on that. That takes me to the trend analysis wizard. I'm going to analyze sample data that we have sampled with the product. You're going to want to use that if you do a demo or an evaluation early, because it's going to take some time before you have enough data that we can even use. And by some time, I mean minimum of 2 weeks. The more data you have, the better the predictions. So ship with some sample data so you can sort of see what see it in action before you have to run for a while. We allow you to filter it in ways you want based on the criteria we talked about: CPU, disk. If you want to eliminate some of the SQL statements from your consideration. There are wanting it for a particular, if you're looking for a particular thing. This is another option I usually use. You can just take them at the defaults. The future releases will make more of this. More of this will be automated, and more of the selections will be more at advanced configuration. This is another filtering screen for a user. If you want to exclude certain users or include certain, only look at certain users, you can do that as well. Finally, how you're going to sort the data. So really the information for all the SQL statements, we're sorting based on a percentage increase, but again, you can sort increasing or decreasing based on any of these columns, total increase. All you have to do is click on it, just like in Excel or Outlook. Select any of the statements, then we'll give you a more deep information about it. Again, if you have quant interpreting it, the text box here will tell you exactly what the meaning of this particular line is. 11% of the total cost of the SQL statement is currently incurred by 1/7/2009. The cost of the statement will have increased by 195.33%. If we want to let our local I/O per second, we can do that. Look at the this is something that has a exponential increase and a linear increase in execution, so it's particularly a problem. And also advanced details here if you want to actually look at the very detailed statistical analysis of it. But you can also do more any criteria, CPU time, elapsed time, discrete physical I/O. If you say that's great, you say lots of I/O is great, but I want to use elapsed time, you can certainly do that for any of the predictions. So at this point, we can actually, I can't launch SQL Optimizer from here, but I don't know if I have the latest license ID there. So exit application sharing, and I'll turn it back over to Sean.
At this particular time, we'd like to open it up to questions and answers. To ask a question, type your question in the chat console online and use our Q&A panel. You can alternately raise your electronic hand, and we'll be able to unmute your phone line to ask your question. So it looks like you did such a fantastic job that there's no questions. Everybody looks up. I saw something. No. Anything? Okay, it looks like we have a question from Ron Holiday. He's interested in getting the slides. So we can email those directly to you the presentation here. We have your email address through the registration, so Ron will email you the slides concluding the presentation. Okay, without any further questions, we'll move it along. If you'd like to view this webinar, you can go to our website, programmers.com/quest. We will have this webinar recorded for your viewing. If you would like to join us on a future webinar, Spotlight on Messaging Performance, we'll hold that on October 29th at 2 p.m. Please register at programmers.com/quest. We'll have an additional webcast on November 19th at 2 p.m. Spotlight on SQL Server Performance. Again, visit our website if you're interested in registering for these webinars. If you have more information on this Quest solution or any of the other solutions in application management, Windows management, virtualization management, or database management, please call in at 1-800-221-7710. You can register for an evaluation special by phone or email. Email address there. And for all the attendees today, log in and download the Quest Spotlight product. You will be entitled to receive a free one-on-one web consult. Please call into the 800 number and contact one of our representatives, and we'll set you up with that one-on-one evaluation special. On behalf of Programmers Paradise and Quest Software, I'd like to thank you for attending today's webinar and hope to see you on future webinars. Thank you.